So you can see that there's these huge computer systems that are being designed, and you can say, well, if it, how do you build these really big systems? So what I wanted to do is talk a little bit about sort of the design process that you would use if you were a digital systems engineer, but you went to work for an Intel or a Motorola or an AMD or an ARM or something like that. Then I have a couple demos right at the end of a working beta. So, hardware description languages, they are sort of like what Java and Python are to assembly language. They give us the ability to leave a lot of the details, the low-level details of hardware design to essentially a compiler. And what I want to do is to sort of give you a sense of how that works and show you a couple of examples, and we'll go from there. So at the end, if you're trying to design something, the first thing you need to always start with is a specification. And it's important to have a specification because most of the interesting parts of a design have to do with making the right trade-offs. If you have to meet a certain power envelope or a certain performance level or a certain cost target, you need to know those at the beginning because you'll make different design choices. And so without a firm specification, it's hard to make good trade-offs, and then you just sort of get mishmash coming out the end of the design process. So we have all these engineering goals that we're trying to achieve, and what we want to do is to come up with some way of specifying those goals, hopefully not just on the back of an envelope, but in some reasonably formal way that could actually be useful in the design of the actual circuit. So, and I'm going to show you how to do that. The other part is that most circuits require the effort of many, many people, which means that you need to figure out some way of partitioning the design process so that 10 or 100 or 1,000 people can work on it rather than just 1 or 2. And the way that's often done is that you break those big chips into modules. There's some caches, there's processor cores, there's communication networks, there's memory interfaces, this long laundry list of things that need to be designed. And if you spend the right amount of time right at the front designing the specification about how each of those components work, not the implementation, but the memory address. I'll send the memory. I'll send it an address, and it will return to me a piece of data within 3 nanoseconds. The details are up to the design team, but they know what they have to accomplish with their design. And so the specification may include, burn no more than 0.2 of a watt. Make sure it can work, with a 1 gigahertz cycle time, so forth and so on. So the idea is to come up with a way of documenting the behavior that you want out of each of the components, and then with enough detail that you can sort of answer all the questions. What does it do in this case? What happens if I send it, this address? Does something different happen? So these are all, details of the implementation that you want to capture. And if you do that, then you can have many design teams. Some of them are working on the software, some of them are working on the hardware. In modern processors, it's often the case that a day after the test chip comes back from the foundry, people are booting Windows and Linux on it. Right? In other words, they've done all the work ahead of time. And mostly this is enabled by having these very accurate descriptions of the behaviors that we can simulate in software. Okay, so we're going to come up with a way of specifying a behavioral model, not an implementation. JSIM is an implementation, right? You're describing gate by gate how to do something. Your job was to sort of test to see if it met all the right behaviors, right? We have a test jig that sort of does that. What the suggestion is that we change that design process the other way around. We start off by describing in complete detail the behavior that we want, and that will serve as a very accurate specification for of what we want the implementation to do. And the neat thing, so the way we do that in the modern world is these hardware description languages. I'm going to show you some simple ones, nothing as sophisticated as BlueSpec. But these are in common use for many types of digital systems design in the current era. So HDL is hardware description language. And remember, what we're trying to do is describe the behavior, not the implementation. So when I show you some examples, keep asking yourself, is this the behavior or is this an implementation? And sort of try to understand the difference, the distinction I'm trying to make. So this behavioral model would let you answer any question. If I'm in user mode and the supervisor, and I get an interrupt request and I'm in the middle of a branch delay slot, what should happen? The answer is, well, I could go to the behavioral model and the system architect would have put the correct behaviors in the model, so I can use the model to answer all these sort of detailed questions. The real motivation behind doing this, or the other motivation behind doing this, besides from just being very specific, is the ability then to take the behavioral specification and give it to a compiler and let it turn out all the low-level gates, figure out what gates should be and things like that. So the process that we're sort of looking forward to is, instead of operating here at the implementation level, so in JSIM you basically typed in gate by gate what the circuit should do, what instead we're going to do is provide a behavioral description of what we want the circuit to do, along with constraints about it has to fit in this much area, it has to burn this much power, it has to have this such and such a cycle time, and we'll turn all of that over to the compilers. So they're going to be figuring out, can I get away with a ripple carry adder, or do I need a carry select adder, or carry look ahead adder? How complicated does my adder have to be? That'll be the question. That question will be answered by the compilers, not by the designers themselves. So what I want to talk about today is basically this piece of the process. As you take some of the more advanced courses, particularly in the VLSI area, the very large scale integration area here, and we have some very nice labs and graduate courses in that area, you can learn more about the design tools, how they take a description of all the logic that you want and turn it into an actual physical artifact. And you'll get some hints of that when I show off a little later on. You'll sort of see that one of the possible compilation targets are these field programmable gate arrays, which I'll show you here. I want to spend a little bit of time sort of talking about this piece. These tools are quite good, just as no one in the modern world writes much in the way of assembly language. The C compilers will do a much better job than you can at optimizing, coming up with just the perfect program, doing all sorts of fancy optimizations about loop unrolling and reduction in strength of operators, all the things that would make your program run a little faster. The compilers know how to do. The same thing is true here. The circuit compilers these days are quite sophisticated. You can do something straightforward, give a little truth table for the logic function you want to implement, and it'll be up to the compilers to figure out what combination of the gates does that in the smallest area or the fastest performance or with the least power. And as most of you are getting into it pays in life to be lazy, right? So it's certainly us 6.3s, we don't actually do hard work, we write programs to do hard work. And so this is definitely an example of that. Designing a highly optimized circuit is not only hard work once, but then you have another circuit, you have to do it again. At some point you say, why don't I just write a program to do that? And that's sort of what's happened here.